Okay, so R of t has to be this, and all this says is that the x velocity is constant and it starts someplace at t equals 0. Okay? And all this says is you have uniform acceleration in the y direction. There's an acceleration that I've written as negative a. The negative a times j. Okay? Now, in this case, the acceleration, if we talk about free fall, is the acceleration of gravity, right? Okay? So, well, I'll work that in a second. Probably should have done that initially, but keeping it general. For something with a downward acceleration, no specific, so I probably should have used the specific. Okay, so anyhow, okay, so we have this, and we've determined that x of 0 and y of 0 are 0, and v of 0 is v naught I, right? So we can rewrite this thing. So it is Vx of t0, but we just determined that Vx of t0 is V naught I, or that V of 0 is V naught I. So, okay, I should have written it. Vx of t0 is V naught. And Vy of t0 has to be 0. If you plug t equals 0 in here, and I said V of 0 equals, yeah, I didn't write that out right, dr dt evaluated at 0. So the t here should be 0. I'll just write that as 0. Okay, and we then conclude that Vy of t naught has to be 0. So you want to write that out carefully. So R of t is what? It's now in terms of what we have, it's V naught t times I, okay, because Vx of t0 is V naught, okay? And x of 0 is 0, plus except it's minus. Okay? Simplifies to this. So, one question. It's a projectile. If the acceleration is negative 10 meters per second squared times your j vector. Well, in this case, R of t equals, in another condition, I'll squeeze it in here. we'll say V naught is 60 centimeters per second, kind of a typical speed in the range of things that you observe. Okay? Well then, R of t is this. Okay? Now, at the floor, Y of t is negative 1 meter, isn't it? I'm going to anticipate the fact that since this is in meters per second squared, and I could have done it in centimeters per second squared, okay? If the acceleration of gravity is negative 10 meters per second squared, then how many centimeters per second squared?
Negative 100.
Huh?
100?
Well, 1 meter would be 100 centimeters, right? So you place 1 meter but 100 centimeters, you get 1,000, don't you?
Oh. Yeah.
Yeah, I know. Okay. Okay. So we could have done this at negative 1,000 centimeters per second squared, or if you're using 9.8 meters per second squared, it'd be 980 centimeters per second squared, right? So you want to lock that in, and yeah, you knew what to do. Okay. So I'm going to, in any case, since this is in meters per second squared, I'm going to change 60 centimeters per second to 0.6 meters per second. And that's your I component. At the floor, so that at the floor, negative 1 meter times J equals negative 5 meters per second squared times J. And it's times t squared, and it's times t squared here. And did I not have t squareds on this thing before? Yeah, I think I did everywhere else. Okay? So the t, guess what? It's a square root of one-fifth of a second squared. Just divide both sides by the negative 5 meters per second squared. Okay? And 1/5 is 0.2, and the square root of 0.2 is about 0.44. That's approximately 0.44 seconds. Now what I told you to use in analyzing the lab was just 0.4 seconds. Assume it takes 0.4 seconds. Because, well, that's what this rounds off to. Didn't want to worry about the small details, make the calculation easy, give you a picture of what's going on. This is how you formally determine what we did. Okay? Now, this is great, but that thing had a downward velocity that wasn't zero. Okay? So that we're back to our original thing where the initial velocity could be anything. Okay? So we want to ask the question, what happens in the case where this thing is 0. Now, it should be clear that we can easily calculate the position at any time between leaving the incline and the floor using this ROT function, right? Plug in your time and it'll tell you where you are in the X direction, where you are in the Y direction. Okay? And you can also eliminate T between the X and the Y. X equals this, Y equals this. So solve this for T, plug it in here, and you find that position's a quadratic function of time. Or that you find that the R of T function is can be expressed as a graph of parabola. We're going to do that for whole. Okay, it's fairly simple. If you remember pre-calculus. Okay?
There are most people that they're like,
I was getting noise in the hall at 11:45.
It's a weird time.
Huh?
It's a weird time.
I think
Yeah.
I think that there are two.
It's okay. I mean, you know, I'm not always quiet, and I catch myself. So, you got people that have great joy from coming out of class, and they make a little noise. They come and go quickly, as long as they don't stand outside the door, in which case I'll close the door. If they're being particularly obnoxious, I'll close the door with attitude. I won't do that.
You gotta give them a snarky look first, though.
No, I'll just go out and say, hey, you know, then I'll close the door, and if they keep it up, well,
Then you start knocking on the door.
yeah. Then I get a little more insistent. Try not to be a jerk, even though I feel like being a jerk sometimes. Okay, so anyhow, and plus, I can't back that up anymore. You know, there was a limit to how much I could back it up before, but now, you know, I can hurt myself just making a fist, you know. Okay, so, who would believe that it would have any effect anyway? Okay, so anyhow, okay, now, so now, let's just kind of draw a picture of this situation. We've got an incline, okay? And the incline has some angle theta. And a ball rolls down the incline and off the edge and then falls to the floor, right? Okay, so let's let I'll just say at the edge, wherever the edge is defined to be, wherever the ball loses contact with the racket. Okay? So, and so what do we know? Let's say speed at the edge is, again, 60 centimeters per second. Let's see what kind of difference this makes. So it's the same situation, and you got 1 meter. Below. Okay? Well, now, what's V naught? Well, it's 60 centimeters per second. Well, let's just draw a little vector diagram, okay? So here we got a vector of magnitude 60 centimeters per second. That vector has an x component and a y component. Okay, I want to find Vx and Vy. Well, we know that the angle theta is with horizontal, assuming that the tabletop is horizontal, that's kind of implicit. So its angle theta is here, right? Okay? Now, another thing I do, and I recommend it, And I didn't say what theta is. .37 degrees is a nice angle. Okay, cosine of 37 degrees is very close to 0.8, sine is very close to 0.6. Okay? So we're going to make that approximation. Okay, so this angle here would be 37 degrees. And we can just use right angle trigonometry. 60 centimeters per second times the cosine of 37 degrees is going to give us a Vx. And then you might write down 60 centimeters per second times the sine of 37 degrees equals Vy. Well, you could do that, but you'd have to also remember that Vy is in the negative direction, right? Well, what we do is we make the convention, using the circular definition now, that this is our angle. Now I want to call this theta, so I want to go back and not call this theta. Okay? So instead of theta, to avoid confusion, shouldn't be any problem if I call this angle alpha. Very common symbol used for angles. Okay? So you're going to call this angle theta. And if this angle is theta, we don't have to worry about positive and negative. It's automatically taken care of. Circular definition of the sine function is going to give us a negative when we multiply 60 centimeters per second times the sine of this angle. So we don't have to think. And if you're like setting up a computer program, you don't want to have a decision step to determine whether the thing you get from right triangles is positive or negative. You just want to do this, okay? You just want to set your angle up properly, which is very easy to do if you just think to do it. And then it's automatically taken care of and you don't have any decisions, okay? So, so we're going to let theta equals what? Well, and we'll do it in degrees. That's going to be 323 degrees. So that's 60 centimeters per second times the cosine of 323 degrees times I. Okay? And that equals, it's going to be positive, it's going to equal 48 centimeters per second. Okay? And Vy times I. So Vx is .48 centimeters per second times I. Now I wrote this stuff, I don't have time, room to write where, you know, the Vy, which is going to be 36 centimeters per second. At least I don't have room to write it very big. Now if you look at the video, use a magnifying glass, give me a little bit of slack for the fact that the chalk is sort of blunt. You verify that says 36 centimeters per second. You can also verify, if you do it quickly enough before I get it in there, then put the negative sign on it, okay? So, Vy and these are correct to two significant figures, okay? and it's negative. Busy doing the arithmetic and forgetting about the quadrant, okay? So and you don't want to miss that. And typically, I mean, if you've got, you know, you're doing a real situation where you have a real angle that you don't know the sine or cosine of accurately, well, first thing you want to do is you want to kind of estimate what it ought to be. Just look at, you know, visualize or draw the angle on a unit circle and say, okay, the sine ought to be about 0.4 and the cosine ought to be about negative 0.93. Okay? Make sense? Okay? Be more like negative 0.9. I think. Okay, well, I don't really think. Just out the ozone. Okay, you can figure it out. But 0.91 I think is pretty close. Between 0.91 and 92.
I don't remember that
Okay.
at all.
Just have to take the square root of 0.84. Square root of 0.81 is 0.9. Square root of 0.84 is a little bigger than 0.91, 0.92. Okay? Okay, anyhow. So now we have our Vx and our Vy. And of course, that's our Vx of 0 and our Vy of 0, right? So again, we can go back to just want to make sure I use the same notation because that's kind of all over the place with notation. But I'm using x of 0. And I use Vx of t0. T0 is 0, okay? That will be y of 0 plus Vy of 0t minus, and I'm just going to write this, which is 1/2 the acceleration of gravity. Okay? It's also a good idea to sketch your coordinate system just so we know that it's vertical horizontal. Because it isn't always, as we've seen. Okay? So, R of 0 equals this x of 0 and y of 0 both equal to 0. That's intuitively obvious, but you want to include that step because it's not always going to be the origin. Okay? Just to be formally. V of 0 equals and you can work through the details of that, but it's the same thing we did over here. It implies that so we get this, okay? And what we formally do is we take the derivative of this, write it down, and then Vx of 0 equals this, equals whatever we get for the derivative, and then we determine our Vx of 0 and our Vy of 0. Okay? Sometimes it's not as obvious. You want to do that step so you don't forget to do it when you need it. Okay? Okay, so R of t equals what? It equals this. Okay? And now we have our initial velocity in the y direction, which complicates things a whole lot. It's real easy to solve this one. You just have this some multiple of t squared equals something, and solve for t. Now you have a quadratic. Okay? So, well, let's do the easy thing. How long to the floor? And how far in the x direction? So, what do you have to do? What can you tell me about r of t when the ball hits the floor?
Well, if you can figure out how long it takes to hit the floor, you can figure out where it is when it hits the floor.
Yeah. How would you figure out how long it takes to get to the floor?
You figure out when, well, you need to know how far away the floor is from, all right.
Same as before.
You said,
And very, very close to the situation you just did, although we never did a 37-degree angle.
then you just set the y component of position equal to 1 meter.
Negative 1 meter.
Well, negative 1 meter, yeah.
Set it equal to 1 meter, you won't get a solution. Okay? Not for positive t, because these will both be negative, right?
Yeah.
And then, hopefully, pretty quick, you'd realize, oh, duh.
Yeah.
You see me go through a dozen oh, duh moments in any class, right? I'm trying to train you. Okay. Hopefully, it's not too confusing. Okay, and that's not really the reason. But okay, so anyhow, well, yeah, that's what you're ultimately going to do, but we're going to do this more formally. Intuitively, though, that's it. Okay, when is this 0? That's when it is, and then you plug that in to find your x position. Okay? Okay, so okay. So, negative 1 meter equals negative 36 centimeters per second times t minus 5 meters per second squared times t squared. Okay? How do you solve that? Now, among other things, you are going to want to change out to 0.36 meter per second. Or change the negative 5 meters per second squared to negative 500 centimeters per second squared, right? You got to have consistent units, which is another reason you always write down your units, because it's so easy to write things within consistent units and just start doing the stupid numbers. And as an engineer, if you're an engineer, you know, the building falls down, people get killed, you get yelled at, okay? And you don't want to get yelled at. Probably worse than that.
Forget the people dying.
Huh?
Forget the people dying, it's the yelling at you want to avoid.
Yeah. Okay, so anyhow, you get the idea, right? How do you solve that equation? What kind of equation is that?
Quadratic, ain't it?
Yeah, you got to recognize that instantly. You say, okay, it's a quadratic equation. I'm still trying to train my pre-calculus students to see that as a quadratic equation. I'd say, okay, all my t's are over here, let's see. I'll just throw them all out and do something.
I'll wait.
I'll try to torture this into something I can solve using the techniques for linear equations, right? No, recognize it's quadratic, then it's easy. Okay, so you can check. I mean, this equation becomes 5 meters per second squared t squared plus 0.36 meters per second times t minus 1 meter equals 0. So t equals negative 0.36 meters per second plus or minus the square root of the square of this. The square of 0.36 is 0.1728. Okay? And that's just because it is. It isn't. It's 12. Okay, 30 and 6, 1296. So that'd be 0.13 squaring this, meters squared over seconds squared. Minus 4ac, but of course you got a negative here, so that's going to be plus 20 meters squared per second squared. Okay? And that's all over 2 times 5 meters per second squared. And you get meters squared per second squared from this and this, because that's got a meter, that's got a meter over second squared, right? So it's very straightforward, just do it. And then think about what it means. Okay, so you get negative 0.36 meters per second plus or minus, you know, that 0.13 makes almost no difference with a 20. If you go to two significant figures, it's not going to make any difference. So you're going to have plus 4.4 meters per second. Now, that's very approximate, but you know, you see that as something we got over there. We got the 0.44. It's a 0.44. Well, if you multiply 2 times 5, you get 10. Most of you know that. You get 10 meters per second squared, and you do the arithmetic. Okay? And you end up with approximately 0.4 seconds, or negative 0.48 seconds. Wait a minute. And this should be 10. Yeah. That's 0.48. Why should that be bigger?
Negative
Hang on a minute.
4.8.
Hang on a minute. There's got to be that.